Hi there, my name is Dr. Pete Davis. I'm a consultant in diabetes and endocrinology at Sandwell Hospital, and I've been giving this lecture entitled Clinical Endocrinology on behalf of the University of Birmingham for probably about 12 years now, and I figured it was about time for a bit of a change. So what I've done is I've broken the lecture into 5 parts. This is the first part where we look at principles of endocrine physiology and we go through the scope of what we're going to cover in the entire series. In the second, we're going to look at pituitary disease. The third, we're going to look at adrenal disease. The fourth, we're going to bracket together gonadal and calcium metabolic problems. And I'm going to finish up with a short summary with some extension questions as well. What's not included is thyroid disease, because that's covered next semester, and a bit of an oversight, I think, from the perspective of common endocrine problems we see. I haven't been asked by the university ever to include anything about salt and water metabolism, but I'm sure that that features in other areas on your course. So the first thing to say is that endocrine glands do not operate in isolation. They operate as coordinated endocrine axes. The next thing to say is it really does help for you to understand the nature of the hormones that you're considering in clinical settings. There's a rich variety of types of hormones, and some of their properties can be predicted by understanding the type of chemical that you're thinking about. Next thing is to think about how hormones operate according to circadian rhythms, and that can be quite important to understanding, for instance, the significance of an individual blood test result. Prolactin, for example, gets released as a series of about 7 or 8 pulses throughout the day, so you can just get lucky and hit a pulse when it's actually particularly high. You could recheck it an hour later and find it's completely normal. The next set of maxims relates to how we investigate endocrine disease. There are a couple of important maxims to remember. If you're considering an endocrine gland failure, do a stimulation test. If you're considering a hyperfunction state of an endocrine system, consider a suppression test. And then we have this hierarchy of testing where we screen, we do some tests which confirm diagnosis, and we may need to do a third set of hierarchical tests that differentiate which sort of disorder we have within endocrine systems. So there you go, it's about axes, not about glands in isolation. Don't forget that stimulatory hormones are trophic as well. That word, of course, relates to growth, and you may remember that from A-level biology, perhaps. So if the stimulating hormone is lacking for some reason, endocrine glands can involute. That means they shrink and they go away to nothing. The next principle is that endocrine systems operate in negative feedback loops, which we'll look at in some detail. This gives them a sort of a property you can consider as self-righting or self-regulating. And a good example of that, which we won't otherwise come back to until next term, will be the thyroid axis. So here is the hypothalamic pituitary thyroid axis in this picture. So the thyroid gland in the neck makes its main secretory products, thyroxine T4 and triiodothyronine T3, and it does so in response to stimulation of TSH. If TSH isn't there, if it wasn't there, the gland would involute and you'd have what we call secondary hypothyroidism in that instance. So TSH makes the thyroid work. Thyroid hormone that's produced feeds back to the pituitary. It also feeds back to the hypothalamus and switches off production of TSH and in turn TRH as well. So the system self-regulates. All this breaks down in thyrotoxicosis. In thyrotoxicosis, the thyroid in an autonomous way makes lots and lots and lots of thyroid hormone. as shown on the slide. That feeds back to the pituitary, and that accounts for why TSH levels in thyrotoxicosis are completely suppressed. The reverse happens in underactive thyroid. In this case, the thyroid is obliterated by autoimmune disease. It stops making T4 and T3, so you lose the negative feedback to the pituitary and to the hypothalamus, and TSH levels go very, very high. Negative feedback in action. So it's great to be off to a good start. That gives you a bit of a grounding about endocrine physiology and some principles to hang your hat on when thinking about endocrine systems. Next off, we've got the rather meaty section of pituitary physiology and pituitary disease. See you there.